So we are moving on to Unit 2, which had the theme of smell. We covered chapters 6, 7, and 8 in this unit. This unit established an understanding of molecules through tangible experience. You began examining smells and molecular data for several compounds. Then you formulated a hypothesis based on patterns in the data that relates smell and molecular structure. You continued to test and refine your hypotheses throughout the unit while exploring molecular formulas, Lewis dot symbols, structural formulas, polarity, molecular size and shape, and bonding patterns. You also learned how to identify specific functional groups within a molecule. Lastly, you looked at the theory for how molecular shape and structure is related to the smell of a molecule and how the olfactory system works to interpret the smell that a molecule has. So that was an overview of the entire unit. We're going to focus on just chapter 6 for right now, which was called Speaking of Molecules. And we started our investigation into chapter 6 by taking a look at several different substances which we had the chance to smell, and we categorized them into categories like sweet and putrid and fishy and minty. Initially were the 4 categories we started with. And initially it looked like we could relate the smell category to the molecular formula. And the molecular formula was really just a summary of how many atoms and what atoms are in the molecule, right? So what type of atom and how many. So in CH4O, that molecule has 1 carbon, 4 hydrogens, 1 oxygen. It tells me nothing about how they're bonded, nothing about how they're arranged, just tells me a summary of what atoms are there. And it looked like initially we could say that if something had 1 oxygen in the molecular formula, it was going to be minty, and 2 oxygens was, and 1 nitrogen was going to be fishy. But ultimately, we came to sort of a conundrum when we smelled another set of molecules, and we saw that 2 molecules that had the exact same molecular formula smelled very different. One was sweet smelling and one was putrid smelling. So this led us into a discussion about isomers, which then led us into a discussion about structural formulas. So the real difference between a molecular formula and a structural formula is that a structural formula is telling me something about the structure. It's a little more informative than just a molecular formula. It's not only telling me what atoms I have, what elements and how many, but how are they arranged on the molecular level? In other words, how are they bonded together? Structural isomers are 2 or more compounds that have the same molecular formula, meaning same number and type of atom, but different structural formulas. Different structures, different bonding configurations, different connectivity of the atoms in terms of how the atoms are connected. So these 2 examples would be structural isomers of each other, right? Same number of carbons, hydrogens, and oxygen, but bonded in a different configuration. These 2, butane and isobutane, would be isomers, and 1 propanol and 2 propanol would be isomers of each other. And we worked a lot on being able to tell the difference between, are these 2 things isomers, or are they the same molecule but they're drawn weird so they look like they're isomers, or are they not isomers at all? So we should feel comfortable taking 2 molecules and saying they're either identical or they're isomers or neither. A structural formula we defined as something that shows the connectivity, right? Not conductivity like we saw in chapter 5, but connectivity of the atoms in the molecule, how they are bonded together. And really, technically, structural formula does not show dots. So all of these things here, these 4, would be structural formulas. Technically, these 2 would be considered Lewis dot structures because they're showing the valence, the lone pair electrons as dots. So these would technically only be the structural formulas. We then looked at Lewis dot symbols and the Hank rule, which allowed us to really easily determine how atoms are going to covalently bond together. So remember, ionic bonding, ions, atoms are losing or gaining electrons, then the ions are balancing each other out. Here we don't have ions. We're looking at covalent bonding, which is where atoms are sharing electrons, so we have a different rule, not rule of 0 charge, but the Hank rule to help us determine how atoms are going to bond together. And the Hank rule essentially says that for hydrogen, oxygen, nitrogen, and carbon, each of those are going to form 1, 2, 3, and 4 covalent bonds respectively. And we further developed this into saying it's not only hydrogen, oxygen, hydrogen, carbon, but it's hydrogen and the halogens, or group 17, oxygen and its group, group 17, nitrogen and its group, group 15, and carbon and its group, group 14, because they have the same number of valence electrons. Now, the number of covalent bonds that they're making ultimately has to do with the number of valence electrons they have and how many they are willing to share to have 8. So carbon and its group has 4 valence electrons, which means they are willing to share with other atoms 4 additional electrons to have 8, which is why they can make 4 bonds. Nitrogen needs 3 more electrons to have 8, which is why they make 3 bonds. Oxygen needs 2, fluorine needs 1, and again, it works for all of the elements in their group. Hydrogen is sort of the loner and an exception to the octet rule. It bonds once because it's okay with just having 2 electrons. Remember that 1 valence electron is in the first shell, and that first shell can only hold 2, so it's stable with those 2. All right, an example here. Which of the following structural formulas is incorrect and why? So you should pause the video and take a look at those 4 structural formulas, and you can pick out which one's incorrect and then unpause the video to see if you got it correct. So the incorrect structural formula is this one. This carbon right here is bonding 5 times, which it's not going to do. Carbon bonds 4 times. So this molecule is not following Hank, where the other molecules are following Hank for their respective elements that are in those molecules. Let's practice drawing some isomers. So let's take the molecular formula C5H12O, and let's see if you can draw 5 possible isomers that exist for this molecular formula. I'll get you started with 1 just to review the process of drawing these guys out. Remember we said the easiest thing to do, keeping Hank in mind, is to connect all of your carbon atoms together first because they bond the most amount of times. Then add your oxygens or nitrogens. I'll put this oxygen on the end here. And then go ahead and add your hydrogens wherever we need them. Now remember, we're going to make sure we are following Hank. That's why I only added 1 hydrogen here. If I started adding hydrogens above and below the oxygen, then oxygen's not following Hank anymore. So there's a lot of rules at once that we're trying to play with. Hank is important though, so make sure that as you're bonding these atoms together covalently, all of them follow Hank. Stop and make sure octet rule is being followed by the atoms that are going to follow it. Hank is being followed, and that would be an appropriate isomer for that molecular formula. See if you can pause the video and draw 4 additional isomers for that molecular formula, and then you can unpause and I will draw a couple more. So let's see what other isomers we can draw. Now, I cannot put the oxygen there. Putting the oxygen there does nothing more than just flip this molecule that we have already drawn, and that would be an identical molecule, not an isomer. The connection of the atoms, though it may look different on first glance, is not actually different. So we want to make sure that I'm connecting the atoms in a different way. And I can do that by placing the oxygen here. That would be different. And then hydrogens all around where we need them, right? That would be 1 isomer. We can also put the oxygen somewhere in the chain of the carbon atoms. It gets no hydrogen because it's already bonding twice, but that would be another isomer. There's so many more than 5 isomers here, but as long as you drew 5 structures where the atoms are connecting differently that are all following Hank and have 5 carbons, 12 hydrogens, and 1 oxygen, then you're good to go for the isomers for that drawing. A covalent bond is a bond that connects 2 atoms together from a sharing of valence electrons. So each of these atoms on their own have a certain number of valence electrons, and we saw that covalent bonding was really about pairing those valence electrons up. Of course, to follow the octet rule, which means that the atoms are going to end with 8 electrons when they're done bonding. So here, these 2 fluorine atoms each have 7 valence electrons, this 1 lone one that they're going to share together in what we called our bonding pair of electrons. The other pairs of electrons that the fluorine had before they bonded, they still have after bonding, but they're not participating in the bonding. We call those lone pairs. Those are important to show in a Lewis dot structure because that is going to lead us into shape of molecule. We'll cover that in chapter 7. So you should be familiar with those terms, bonding and lone pair. We included lone pairs to turn our structural formulas into Lewis dot structures. So Lewis dot structures show the unbonded valence electrons in a molecule as dots. And here are some examples here. We went over technically this is what a Lewis dot structure is, but many sources and many textbooks and online sources will say that this is also a Lewis dot structure, and that's fine too, as long as we are showing the lone pairs as valence. As long as we are showing the lone pairs as dots, that's all we care about in terms of drawing a Lewis dot structure. The bonding pairs can be shown as either a line or dots, but if we're drawing a Lewis dot structure, at the least, the lone pairs need to be shown as dots. So those are all examples there. Here are examples of the types of covalent bonds we can form in terms of a single, double, or triple. So, one way that oxygen can satisfy HONC, instead of forming 2 single bonds, it can form 1 double bond. Instead of nitrogen satisfying HONC by 3 singles, it can form a double and a single, or it can form 1 triple bond. And what it means to form a single, double, or triple bond is just the number of electrons that are being shared. So a single bond is 1 pair of electrons, a double bond is 2 pairs, or 4 total, and a triple bond is 3 pairs, or 6 total. And then the last thing that we looked at in this chapter, once we determined that we can't really rely on molecular formula, that we could have the same molecular formula, different smell, which means something about the structure of the molecule is different, we wanted to say, well, what about the structure is different? And it led us into a discussion on functional group. So we ended chapter 6 by saying it looks like if we look closer, if we draw out the structure of a molecule, there are these specific groups of atoms that appear in lots of different molecules that smell similar, and we called those groups of atoms functional groups. A functional group is a group of atoms within a molecule that lends itself to giving specific properties, such as smell, to the molecule, among other things, boiling point, melting point, viscosity, but smell was the property that we were focusing on. And the functional groups that we focus on and you should be familiar with are the ones that are up here: alkanes, alcohols, ketones, carboxylic acids, esters, and amines. We looked at how to identify that the functional group is in the molecule. We looked at what smell category the functional group would have, and some name characteristics. So alkanes, I know it says no functional group. The functional group really is the fact that it's just carbon and hydrogen atoms all single bonded. Propane molecules, their names will end in ane, and they have, most of them, gasoline-like smell. Carboxylic acids, here's their functional group highlighted in yellow. It's a carbon double bonded to an oxygen, single bonded to an oxygen, and H, always found at the end of a molecule. Those molecules are most likely putrid smelling, and they end with ic acid. Esters are very close in terms of what their functional group looks like, so we have to be careful comparing it to carboxylic acids, We'll get those confused. Those molecules tend to smell sweet. They have 2 parts to their name. The first part ends in YL, ill, and the second part ends in ate. And we'll recognize an ester functional group. It'll look very similar to a carboxylic acid. It's C double bonded O, then single bonded O, but this single bonded oxygen is bonded to another carbon in an ester, where here it's bonded to a hydrogen. So this functional group for carboxylic acid is found at the end of the molecule. This one's found somewhere sort of in between, if you want to think of the other carbons. Ketones end in -one. It's a carbon double bonded to an oxygen. That's the functional group for a ketone, somewhere in the middle of the chain. They tend to smell, this says sweet, but most ketones smell minty. So we'll add that category here. There are some exceptions. This is a simple smaller ketone. The larger they get, the more minty they smell. Alcohols end in -all. They tend to smell medicinal, right? We said like a doctor's office. Think of like rubbing alcohol, isopropyl alcohol. The functional group is an oxygen and a hydrogen, the OH. And then amines is when we have a nitrogen in a molecule. They tend to smell fishy, and those names are easy. They end in amine, just like the name of the functional group itself. So here's a chart that sort of summarizes what we have seen not only in chapter 6, but there's going to be some skipping ahead to chapter 7, because remember, we then developed the idea that not all alcohols smell medicinal, not all ketones smell minty, and that's why we're going to see the different categories here. We introduced the smell category of camphor in chapter 7, but we will save that for that review video. The last thing we ended this chapter with was looking at really our first chemical synthesis, right? We looked at the copper cycle, which was really our first chemical reaction or series of reactions, but our first chemical synthesis, which is the creation of a specific compound or compounds through controlled chemical reactions. And by controlled, if we think back to the lab that we did, we took a specific carboxylic acid molecule and a specific alcohol molecule and reacted them together to form a very specific ester. So the idea of chemical synthesis is really cool because we can say, I want to make this, and work backwards to say, if I want to make this one ester, what alcohol and acid will I need to do that? It's not just I can't just take a random alcohol and ester. It's a very specific, if I want to make one that smells like banana, I'm going to need a specific alcohol and ester to do that, or alcohol and acid. If I want to make one that smells like raspberry, it's going to be a different alcohol and acid. Chemical synthesis is an example of a chemical reaction, which is a process that results in chemical change of a substance producing new compounds with new properties. And this was an idea that we continue to develop and expand upon throughout the rest of the year in other chapters. But the obvious new property that we were able to witness here was the property of smell changing. We started with a really, really bad smelling carboxylic acid and alcohol, and ended with something that was notably different. If we didn't see it as sweet, it definitely should have seemed sweeter, but that was the banana odor in the ester that we made in that specific activity, if you remember that one. And we looked at how we can take, in terms of the mechanism here, the acid, in this case this is butyric acid, and alcohol, this is ethanol, and react them together to form an ester. So remember, the same bonds break every single time. We have the OH bond of the acid that breaks and the OH bond here of the alcohol, the CO bond of the acid. So the OH comes off here, the H comes off there. They together will make water, that's H2O. And now that that H and OH are forming water, this carbon and this oxygen are not following Hank anymore. So they will bond to each other to form a new covalent bond that forms a new molecule. And that new molecule doesn't have an alcohol functional group anymore, doesn't have a carboxylic acid functional group anymore. It now has an ester functional group. And like we said before, functional groups give molecules specific properties. So the fact that it's one molecule is losing an acid functional group, one molecule is losing an alcohol functional group, the properties that those functional groups typically have are not going to be seen in this new molecule. It's going to assume the properties of an ester functional group, which is sweet smelling. The name of this is ethyl butyrate. Remember, we named the ester. The first part of the name comes from the alcohol. We drop the anol and we add YL, so ethyl. And then we add 8. We drop the ic acid and we add 8 to the carboxylic acid name, so ethyl butyrate. So that was forming an ester, our chemical synthesis, at the end of chapter 6. That brings us to the end of chapter 6. We'll catch you up with all of the new smell categories we introduced and shapes of molecules in the chapter 7 throwback review video.